Okay, so we're going to start where we left off on the last video. And we talked about how to answer part A, we're going to have to go back and remember some of the chapter 7 things. We're dealing with here a sampling distribution because I have a sample of size 840. So how do I know the shape is normal-like? Well, I'm dealing with means and I have a large sample. So the central limit theorem tells me as long as n is large, my sampling distribution will be normal-like. It'll be centered around the true mean of 280. And the standard deviation, well, we learned that the standard deviation should be, standard deviation, not the mean, the population standard deviation divided by the square root of n, right? So the standard deviation here would be 60 divided by the square root of 840. So if we do this on our calculator, divided by the square root of 840, and that would be about 2.0702, we'll say. Okay, so shape, center, and spread of the sampling distribution, it's normal-like because we have a large sample, and the central limit theorem tells us as long as n is large, sampling distribution is normal-like. Centered around the true mean of 280, and it has a standard deviation of 2.0702, taking that sample size into account. Now, part B says to sketch the sampling distribution of x bar. Okay, so we need to so I can do that on here. If we draw it out, it should be centered around 280, and it wants us to mark the values 1, 2, and 3 standard deviations on either side of the mean. Okay, well, how will I do that? Well, as I go up, I add standard deviations, right? So I need to say 280 plus 2.0702. And so this next one will be 282.07. And then plus 0.0702. And so this will be 282.14. And then the last one plus 2.0702. And that will be 284.21. Sorry, I'm running out of space. Going backwards, I would just subtract the standard deviation. So 280 minus 2.0702. That'll be 277.93 minus 2.0702, so that's 275.86, then minus 2.0702, and that's 273.79 if I round it. Okay, so here I have this sampling distribution, and this is essentially what it's going to look like. According to the 68, 95, 99.7 rule, about 95% of all values of x bar lie within a distance m of the mean of the sampling distribution. What is m? Well, m would be the distance from the mean to 2 standard deviations on either side, right? M equals whatever 2 standard deviations is. Would you agree? Because that's the distance from the mean to either side. So shade the region on the axis that is within m. So that would be here, right? So that would be from 277.93 to 282.14. So m here, if m is 2 standard deviations, is just 2 times 2.0702. So m, the value would be 4.1404, if I doubled that correctly. Whenever x bar falls in the region you shaded, the population mean lies in the confidence interval x bar plus or minus m. For what percent of all possible samples does the interval capture mu? Well, what percent of the time would it capture mu? Well, 95, right? Which makes sense because that's the confidence level. That's how confident I am in capturing the true value. Okay, we're still going to refer to this, and it says, refer to exercise 5. Below your sketch, choose one value of x bar inside the shaded region and draw its corresponding confidence interval. Do the same for a value of x bar outside the shaded region. Okay, so if I pick one inside. So let's say, let's pick 281. That's inside the shaded region, right? All right, and then it says, draw the corresponding confidence interval. Well, the corresponding confidence interval would be that estimate plus or minus 2 times the standard deviation, right? Okay, so 281 plus or minus the m that we calculated in the last question, which the m we calculated in the last question was 4.14. Okay, and so that interval would be 281 minus 4.14. So from 276.86, and then 281 plus 4.14. That would be up to 285.14. Now, did that interval capture the mean? Yeah, 280 is within that interval. In fact, any value you picked in this shaded area would give you an interval that captures the true value. Now, what if we pick a value outside? Let's say 274. That's outside, right? If I do 274 plus or minus m, let's see what interval I get here. So 274 minus 4.14, that's 269.86. And then 274 plus 4.14, that's 278.14. Did that one capture the true mean? No, it did not. So the most important difference between these intervals, as long as my mean that I get from my sample is in this interval, in this range, it's going to result in an interval that captures the truth. If it falls outside this range, it's going to result in an interval that does not. That's where that 95% comes in. 95% of the time, 95% of the samples are going to result in a point estimate that gives us an interval that captures the truth, and 5% of them will give us an interval that does not. Okay, let's just kind of talk a little bit more about generic confidence intervals to tie this all together. All right, so we've talked today that this is the formula that we're going to use to create a confidence interval. Your statistic is your point estimate. It's going to be either x bar or p hat, what we're gathering from the sample. Your critical value is how many standard deviations you're away from the mean times the standard deviation. Now, everything after the plus or minus, this is your margin of error. Okay, the margin of error is the critical value times the standard deviation. Couple of things about that margin of error. The user chooses that confidence level, which is what affects the critical value. So the confidence level changes the critical value. The more confident we are, the larger that critical value is going to be. The more confident we are, then that's going to make a wider interval, which makes sense, right? If I have a wider interval, I'm more confident that I have captured the truth because I have a wider interval to deal with there. The critical value depends on the confidence level and the sampling distribution of the statistic. Greater confidence requires a larger critical value. Now, the standard deviation. What's the one thing that affects standard deviation or variability? That's sample size. So sample size comes in here too that affects our margin of error. Remember, you're dividing by the sample size. So the larger the sample size, the lower this will be, right? And so the lower your margin of error will be. So if I want to reduce margin of error, if for some reason I want the margin of error to go down, I could do one of two things. I can reduce the confidence level, or I can increase my sample size. Now, there might be reasons for doing either one of these things. If I want to keep my confidence the same, I can just increase my sample size, and it still keeps my confidence level the same while reducing the margin of error. Okay, so that's just something to keep in mind. And here it is stated for you. The margin of error gets smaller when either the confidence level decreases or the sample size increases. And so those are going to be the two things that play into your margin of error. All right, couple of things to keep in mind. Number one, our method of calculation assumes that the data comes from a simple random sample, and we have talked about this starting in Chapter 7. It's very important that we have a simple random sample that we're dealing with here. Okay, there are other great ways of sampling, but that's not going to be the one we use here. The second thing, the margin of error in a confidence interval covers only chance variation due to random sampling or random assignment. What I mean by that is your margin of error is not going to tell us anything. It will not help calculate any biases that are present. Margin of error does not show bias. It only shows the error that can happen just due to chance variation that we have happening in sampling. So that's very important to keep in mind, and we'll practice this a little bit more tomorrow. So go ahead and try your practice assignments and let me know if you have any questions.